what if the next hello from an alien civilization doesn't arrive in a traditional radio dish, but as a subtle whisper processed deep inside a server farm? It's a thought that might seem pulled straight from a sci-fi novel, but it's becoming our reality faster than you think. Just last year, while most of us were probably doom scrolling or binging the latest streaming sensation, something extraordinary was happening. A highly sophisticated neural network, diligently working at the Green Bank Telescope in West Virginia, was sifting through an unimaginable 150 terabytes of raw sky noise. This isn't just a lot of data, it's a cosmic ocean of static, interference, and faint signals. And what did this tireless AI find? It flagged 8 distinct signals that, even after rigorous analysis, still look impossible. 8! Not 8 million, not 800. Just 8 incredibly precise, puzzling needles in a cosmic haystack that no human eye, no traditional software had ever managed to notice before. Tonight, we're going to delve into why those 8 whispers matter so profoundly, how artificial intelligence is rapidly transforming every rooftop camera into a planet-wide motion sensor, and why the next blockbuster headline about life beyond Earth might very well be written not by a seasoned journalist, but by lines of code. It's a new era of discovery, one where our machines are becoming our primary senses in the vastness of space and the skies above us. So grab a seat, silence your phone, and let's ask the only question that truly counts. Will AI unlock the next alien encounter? The old way was never going to scale. For 60 years, the search for extraterrestrial intelligence, or SETI, operated with a methodology that was frankly entirely logical given the technology of the time. They did exactly what you or I would do. Point a giant radio dish at a promising star, listen intently for a few minutes, maybe an hour, shrug when nothing obvious appeared, and then move on to the next star. It was a valiant effort, born of scientific curiosity and hope. But it was also inherently limited. The problem, as you can probably guess, is monumental. Space is incomprehensibly big, stretching across billions of light years. Time is equally wide, encompassing billions of years. And to make matters worse, our own planet is a cacophony of electromagnetic noise. Earth's myriad gadgets, cell phones, TV broadcasts, radar systems, satellites scream across the very same radio frequencies that we expect intelligent extraterrestrial civilizations might use to communicate. It's like trying to hear a whisper in the middle of a rock concert. Scientists at Harvard's Galileo project, acutely aware of these limitations, aptly pointed out that even a massive 100-meter radio dish, a marvel of engineering in its own right, is essentially just a drinking straw trying to survey an entire ocean. Imagine trying to understand the full scope of marine life by sampling a few milliliters of water here and there. You'd miss almost everything. We needed not just a bigger straw, but perhaps a million straws working simultaneously, tirelessly, and with an unprecedented level of discernment. And that's precisely where machine learning enters the picture. It's not just another Silicon Valley buzzword, something tossed around in tech conferences. In the context of SETI, AI is the first intern who never blinks, never gets tired, never needs a coffee break, and can process data at speeds and scales that would simply overwhelm any human team. It represents a fundamental shift from episodic, human-driven observation to continuous, machine-powered vigilance. This isn't about replacing human ingenuity, but augmenting it with tools capable of tackling problems of truly cosmic proportions. How AI hears what we miss. So what exactly are these machines listening for? Picture a very specific kind of radio signal. A narrowband tone, incredibly focused, that subtly drifts in frequency, much like the slide of a trombone. That Doppler wiggle is a telltale sign of technology. Why? Because if a signal is coming from a distant planet orbiting a star, that planet is moving relative to us. This motion causes a slight, predictable shift in the signal's frequency, a phenomenon known as the Doppler effect. Natural astrophysical phenomena, like pulsars or quasars, typically produce broadband noise, or signals that don't exhibit this precise, sustained drift. A clean, narrowband signal with a consistent Doppler shift is a strong indicator of an artificial, engineered source. Historically, traditional software used by radio astronomers required researchers to pre-program the expected drift rate. They had to guess, or at least have a strong hypothesis about how fast a potential alien transmitter might be moving. If their guess was off, even slightly, they'd miss the signal entirely. It was like trying to tune a radio without knowing the station's exact frequency. But modern deep neural networks, the kind of AI we're talking about, operate differently. They don't need to be told the drift rate. They learn it on their own. They can sift through the raw data and identify these subtle, shifting patterns, even if they're incredibly faint or follow a trajectory we hadn't anticipated. Beyond just the Doppler shift, these AIs can detect 20 other subtle shapes, modulations, and characteristics in the signals that we as humans had never even thought to name, let alone program a computer to look for. It's like discovering a whole new vocabulary in the language of radio. Consider the groundbreaking work of Peter Moss' team at the University of Toronto. They embarked on an ambitious project, training their neural network on a vast library of known interference. The radio clutter generated by GPS satellites, airport radars, even the hum from microwave ovens in our homes. This taught the AI what not to look for, effectively filtering out Earth's noisy backdrop. Then they gave the net a simple yet profound instruction: surprise us. And surprise us it did. From the 150 terabytes of data from the Green Bank telescope, the AI popped out 21,000 anomalies. Think about that. 21,000 instances where the AI said, hey, this doesn't look like anything I've been trained on, and it doesn't look like natural noise. Of those, after rigorous sanity checks and further analysis by human experts, 8 signals survived every test. 8 signals that, for now, defy conventional explanation. Now, it's crucial to note that these 8 signals haven't repeated yet. This is a key point in SETI. A one-off signal is hard to confirm. But here's the kicker. This algorithm has just started its work. The initial survey that yielded these 8 candidates covered only 820 stars. Today, the survey has expanded dramatically, now encompassing 3.2 million stars. Do the extrapolation. If you found 8 potential technosignatures in 820 stars, what happens when you scale that up to 3.2 million? The math suggests we could be looking at 31,000 candidate signals waiting in the queue, just waiting for follow-up observations and verification. These are still incredibly tiny odds in the grand scheme of the cosmos. But for the first time, the limiting factor isn't how long can we stay awake and stare at a screen. It's how fast can our GPUs inhale and process this mountain of data. This isn't just an improvement, it's a revolution in our listening capability. The sky next door. While radio hunters like Peter Moss' team are staring outward, deep into the cosmic ocean, another entirely different kind of AI is staring up from right above your neighborhood. This isn't about distant stars. It's about our own backyard, our own atmosphere. Meet the Galileo Daylight camera. It's a donut-sized dome perched on a rooftop at Harvard. Inside this unassuming dome, an array of infrared eyes refreshes every single millisecond. This constant, high-speed stream of data is fed directly into a sophisticated YOLO, or you only look once, neural network. But this AI isn't trained on identifying cats and dogs, or even cars on a street. Its training data includes bats, flitting through the night sky, high-altitude balloons, tiny insects, and commercial Boeings. It learns to recognize all the common, mundane objects that populate our atmosphere. The results from its initial operations are no short of astonishing. Over a period of just 5 months, this system detected and tracked 500,000 objects. Of those, a staggering 62,000 didn't match anything on the FAA registry, meaning they weren't known aircraft or drones. And here's where it gets truly interesting. 16% of those unregistered objects moved in ways that fundamentally broke straight-line physics. We're talking unexplainable accelerations, sudden stops, and impossible turns. To put that into perspective, that translates to approximately 2,400 objects every single month that we simply cannot name, cannot explain with our current understanding of atmospheric phenomena and known technology. Now, let's be clear. Most of these will eventually turn out to be sensor glitches, atmospheric ice crystals reflecting light in unusual ways, or perhaps even exotic but terrestrial drone prototypes. The scientific method demands we exhaust all conventional explanations first. But some of these observations have already forced researchers to ask genuinely perplexing questions, like, why did that blob execute a 90-degree turn without a sonic boom or any discernible propulsion system? The beauty of AI in this context is its impartiality. It doesn't get excited. It doesn't jump to conclusions. It simply timestamps the weirdness, meticulously recording every anomalous data point. This objective, verifiable record ensures that humans can't memory hold it later, can't dismiss it as a fleeting illusion or a misremembered observation. The data is there, raw and undeniable, waiting for human analysis and hopefully explanation. The system also highlights the need for additional sensor data, such as triangulation for distance measurements, to better classify these ambiguous objects and resolve their true nature. The data fire hose meets the algorithm. The sheer volume of data being generated in the search for cosmic signals is mind-boggling. Breakthrough Listen, one of the most ambitious SETI programs, currently harvests an astonishing 30 terabytes of data per day from just one of its telescopes. That's enough data to fill thousands of high-definition movies every 24 hours. And this is just the beginning. The Square Kilometer Array, a colossal international project set to switch on next year, will elevate this data deluge to an entirely new level. It's projected to hit an exabyte. That's a billion gigabytes every few months. To put that in perspective, an exabyte is roughly equivalent to all the words ever spoken by humankind. No human biology, no matter how many researchers you throw at it, can swim in that river of information, let alone make sense of it. This is where AI becomes not just helpful, but absolutely indispensable. Researchers are increasingly leaning on advanced techniques, like unsupervised clustering. Imagine dumping every single piece of raw data, every radio blip, every flicker, every bit of noise, into a massive digital cauldron. Then, instead of telling the AI what to look for, you instruct it to find its own patterns, to let structure emerge organically from the chaos. These are called self-organizing maps. The AI then groups similar signals together, signals that cluster near known interference sources, the aforementioned GPS, radar, microwave ovens, get efficiently binned and discarded. They're recognized as terrestrial noise. But those lonely dots, those outliers that don't fit into any known cluster, that stand apart from the familiar noise, those become the VIP guests, the signals that demand closer inspection, the potential whispers from beyond. This same playbook, this methodical, data-driven approach, is now being recommended by none other than NASA for UAP hotlines. They're advocating for multi-sensor alerts, combining radar, infrared, visual, and acoustic data, along with machine-readable metadata. Crucially, they're pushing for zero human adjectives. What does that mean? It means stripping out subjective language, emotional interpretations, and anecdotal descriptions. Instead of "it looked like a saucer and moved impossibly fast," the data would simply record its precise trajectory, velocity, spectrum signature, and sensor readings. Why is this so important? Because when you strip out the adjectives, you strip out the stigma. When you remove the sensationalism and the personal biases, suddenly the topic isn't fodder for dinner party jokes or late-night talk shows. It becomes pure data, ripe for scientific inquiry, making it far easier for serious researchers to engage without fear of ridicule. AI is helping us make the extraordinary ordinary, simply by presenting it as verifiable data. Why 2025 feels different. The year 2025 isn't just another year on the calendar. It feels like a pivotal moment, a quiet turning point in humanity's collective gaze toward the unknown. Consider these developments, which, while not screaming aliens in bold headlines, collectively signify a profound shift in how we approach the search. In April, the U.S. All-Domain Anomaly Resolution Office, or AARO, quietly adopted the Galileo data format as its official standard for UAP reporting. This isn't just bureaucratic paperwork, it's a monumental step toward standardization. It means that observations from different sensors, different locations, and different agencies can now be seamlessly integrated and analyzed, speaking the same digital language. This move legitimizes and formalizes the collection of UAP data on a national level, bringing scientific rigor to a topic long relegated to the fringes. Then, in May, the European Space Agency, or ESA, announced something equally significant. They're adding anomaly detection modules to every new Earth observation satellite they launch. Think about the implications. Our planet is now being continuously monitored, not just for climate change, deforestation, or urban sprawl, but actively for anomalies, things that don't fit the expected patterns. These new eyes in the sky, powered by AI, are designed to spot unusual objects or phenomena in our atmosphere or near-Earth space, adding another layer to our emerging planetary sensory network. And in June, the Japanese Space Agency, or JAXA, launched a CubeSat, a tiny satellite whose only payload is an AI chip specifically designed to listen for fast radio bursts in the VHF band. Why is this particular frequency significant? Because the VHF band is a part of the radio spectrum that Earth has a largely banned for terrestrial transmitters due to its interference with critical communication systems. This means that if the JAXA CubeSat detects a fast radio burst in this band, the likelihood of it being human-made interference plummets dramatically, making any detection incredibly compelling. It's a targeted search in a quiet corner of the radio spectrum, far from our own noise. No single press release screamed aliens when these events occurred. They were, in isolation, technical advancements or policy updates. But together, they form something far greater. A nascent planetary nervous system with AI acting as the central spinal cord. For the first time in human history, every major continent, every significant space agency is beginning to watch the sky with the same, or at least compatible, open source software and standardized protocols. This collective vigilance means that if something truly anomalous appears over Tokyo, and then, a mere 8 minutes later, is observed over Los Angeles, the time it would take for an object moving at incredible speeds to traverse that distance, we won't just have isolated reports. We'll have correlatable, machine-verified data from multiple, independent sources, making denial or dismissal far more difficult. It's a game changer for confirming widespread, genuinely unexplainable phenomena. The false positive paradox. It sounds counterintuitive, doesn't it? More data should, by all logical reasoning, lead to more false positives. If you're looking at more things, you're bound to see more errors, more mirages, more sensor glitches. Yet, what we're witnessing in this new era of AI-driven exploration is the exact opposite. The key lies in something called Bayesian priors, a statistical concept that essentially means updating your probability based on new evidence. Each new sensor, each additional layer of data doesn't just add more information, it sharpens our prior beliefs, making our assessment of the probability of a true positive far more accurate. Consider this. A single blip on a radar screen might be a bird, weather, or a calibration error. It's a low confidence event. But what if that same blip shows up simultaneously on radar and on an infrared array and on an acoustic sensor network and is visually confirmed by a high-resolution camera, all cross-referencing in real time? Suddenly, the probability of it being a false alarm plummets. When you have multi-sensor corroboration like that, the false alarm rate drops to something almost unfathomable, perhaps 1 in 10 trillion. It's like having a dozen independent witnesses, all with different perspectives, confirming the exact same improbable event. Once you cross that threshold of incredibly low false alarm probability, the burden of proof flips entirely. Instead of requiring extraordinary evidence to prove something is technology, you now require extraordinary evidence to claim it isn't technology. The default assumption shifts. If something is behaving in ways that defy known physics and is detected by multiple independent AI-driven sensors with near zero false positive rates, the simplest explanation might just be that it's something truly advanced and unknown. And here's where AI truly shines. It makes that flip possible in milliseconds. Humans would still be filling out the paperwork, coordinating sensor logs, and trying to reconcile conflicting reports. AI, with its ability to instantly cross-correlate vast streams of disparate data, performs this complex Bayesian analysis in the blink of an eye, presenting a consolidated, high-confidence assessment. It moves us from anecdotal observation to actionable, statistically robust evidence almost instantaneously. Meet the new detectives. The front lines of this new search aren't manned by grizzled prospectors with telescopes, but by brilliant scientists wielding algorithms. These are the new detectives, each specializing in a different aspect of the cosmic mystery. Take Dr. Simona Vietri from the Naples Observatory. Her specialty? Training neural nets to spot incredibly faint, incredibly fast laser pulses, signals lasting a mere billionth of a second. Why laser pulses? Because some theories suggest that advanced civilizations might use focused laser beams for interstellar communication rather than broad radio waves, precisely because they can transmit vast amounts of data with less energy over long distances. Detecting such fleeting, precise flashes requires an AI capable of operating at the very edge of our sensory perception. Then there's Dr. Cheng Liu from Tsinghua University, who developed what he calls a ghost filter. This ingenious algorithm removes the telemetry signals from the Chinese space station, a significant source of radio interference, without ever needing to see the station's blueprints or understand its internal workings. How does it do it? The algorithm reverse engineers the waveform itself. It learns the unique signature of the Chinese space station's transmissions by observing them, and then it can subtract that pattern from the overall noise, leaving behind a cleaner signal for analysis. This is crucial for clearing out the clutter of our own space activity. And consider Dr. Karen Solins at MIT. Her work addresses the overwhelming data volume head-on. She stores only the difference between what her AI model expects to see and what actually arrives. Instead of archiving petabytes of mostly empty or predictable data, her system only saves the anomalies, the unexpected deviations. This shrinks the storage requirement from petabytes to mere gigabytes before any human even touches the data. It's an incredibly efficient way to manage the data fire hose, ensuring that only the truly interesting bits survive for human inspection. None of these brilliant minds are claiming they found aliens. They are scientists grounded in evidence and rigorous methodology. But all of them articulate the same fundamental truth, a sentence that echoes the paradigm shift we are discussing. We finally have tools that don't assume the answer before we look. This is the core of AI's contribution. It allows us to approach the unknown with truly open eyes, free from our human biases and preconceived notions of what alien life or technology should look like. The ethical speed bump. If your code, your meticulously trained neural network, finally finds a confirmed techno-signature, a signal unequivocally from an alien civilization, who gets to make the announcement? Who owns that moment in history? Is it the individual programmer who wrote the winning algorithm? The university that hosted the research? The taxpayers who funded the telescope that gathered the data? Right now, the policy surrounding such a monumental discovery is, to put it mildly, a patchwork. It's a collection of academic traditions, international agreements, or lack thereof, and institutional guidelines that were never designed to handle something of this magnitude. The problem is, AI moves at light speed, processing information and making discoveries far faster than any committee can convene, deliberate, and draft a new protocol. The traditional scientific process of peer review, publication, and then public announcement could take months, even years. Recognizing this critical speed bump, institutions like Harvard are already implementing proactive solutions. They now insist that every model they deploy in the search carries a kill switch hash. This isn't a literal switch to destroy data, but a cryptographic signature tied to an automated protocol. If the network's confidence in an anomalous detection exceeds a critical threshold, say 99.7%, then the observation metadata is automatically and simultaneously released to 6 independent groups worldwide. These groups include other research institutions, international scientific bodies, and perhaps even designated government agencies. Why the seemingly drastic measure? Because no single entity, no single nation, no single individual should be able to sit on that kind of data. The only thing worse than a false alarm that ignites global panic is a true alarm, a genuine discovery of extraterrestrial intelligence that is then kept secret, controlled, or suppressed by a select few. Transparency, immediate and widespread, becomes paramount when facing a discovery that could redefine humanity's place in the cosmos. It ensures that such a profound finding belongs to all of us, not just a privileged few. What happens if the phone actually rings? Let's play out a couple of scenarios just for a moment to imagine what might happen if AI truly delivers. Scenario A, the cosmic whistle. Imagine a narrow-band radio whistle, perfectly clean, precisely modulated, and unmistakably artificial. It's detected and within minutes verified by 5 dishes spanning 3 continents, all using AI-driven analysis. The confidence level is off the charts. What happens next? Within minutes of the press embargo ticker beginning its countdown, because even in this scenario, there will be an attempt at an embargo, global stock markets would notice. Cryptocurrency, the ultimate barometer of speculative human emotion, would likely spike wildly, then crash, as people tried to figure out what it all meant. Within hours, every app with push notification rights on your phone would light up with breaking news alerts, overriding your daily routine. The world would stop. Within days, Congress and parliaments worldwide would schedule emergency hearings. Someone inevitably would try to launch an alien coin cryptocurrency. AI won't prevent the initial chaos, the human reaction of awe, fear, and speculation. But here's what it will do. It will timestamp every rumor, every piece of misinformation, every piece of data. This algorithmic chain of custody will make fact-checking trivial. Every claim, every video, every piece of data can be cross-referenced against the original, machine-verified source. The noise will be immense, but the signal will remain clear and verifiable. Scenario B, the silent intruder. Now imagine a blurry, triangular object streaking across the field of view of a Harvard Dalit camera. It accelerates from a standstill to an impossible velocity, pulling 80 Gs, then, without a splash, submerges into the ocean. The AI timestamps it, logs its impossible trajectory, and flags it with maximum anomaly confidence. If that initial metadata packet survives peer review, meaning other AIs and human experts confirm its anomalous nature, the algorithmic chain of custody takes over. Navy sonar archives with decades of passive listening data would be subpoenaed and subjected to AI analysis, searching for similar patterns. If the range of the submergence is within coastal waters, the Coast Guard would be legally obligated to file a marine casualty report, meticulously detailing the unknown object. Either way, the story doesn't die in a forgotten filing cabinet or a whispered rumor, because the algorithmic chain of custody is public, transparent, and immutable. The data, the precise measurements, the impossible physics, it's all there, forcing a reckoning. It ensures that extraordinary claims are met not with dismissal, but with extraordinary, verifiable data. The silence that keeps me up. Perhaps those 8 green bank signals were indeed ghosts, fleeting anomalies that will never repeat. Maybe the 2,400 monthly UAP tracks are, in the end, just balloons, sensor glitches, or exotic terrestrial prototypes we haven't yet identified. It's possible. But here's the unsettling truth. The error bars on the assumption that life is rare just shrank by orders of magnitude. For decades, the Fermi paradox, the contradiction between the high probability of extraterrestrial life and the lack of evidence for it, was a comforting thought for some. The universe is big, life must be rare, and we're probably alone. However, if you run a Monte Carlo simulation, a computational model that uses repeated random sampling to obtain numerical results, with our current detector sensitivity and the new dramatically lower AI-driven false positive rates, something remarkable emerges. The chance that we hit a confirmed techno-signature before 2030 crosses 50%. Think about that. Coin toss odds, 50-50, for the biggest headline in human history. This isn't faith. This isn't wishful thinking. This is Poisson statistics with an updated lambda, a statistical parameter representing the average rate of occurrence of an event. Our lambda, our rate of finding potential signals, has been dramatically increased by AI's ability to sift through noise and identify genuine anomalies with unprecedented precision. The search space has expanded. Our filters are sharper, and our ability to distinguish signal from noise is exponentially better. The odds are shifting, and they're shifting in a way that should keep us all up at night, not out of fear, but out of sheer, exhilarating anticipation. Your place in the loop. You might be thinking, this all sounds amazing, but I'm not a scientist. I don't have a giant radio dish in my backyard. What's my role in all of this? And that's the beauty of this new paradigm. You don't need a multi-million-dollar telescope. You just need open eyes, a curious mind, and perhaps some readily available technology. NASA, recognizing the power of distributed observation and citizen science, has launched initiatives like the SkyHub platform. This allows anyone anywhere to plug a simple $200 RTL SDR dongle into a Raspberry Pi computer and feed real-time radio data directly into the same cloud pipeline that professional astronomers use. Your backyard in Boise, your apartment balcony in Bangalore, your rooftop in Rio, all can become listening posts contributing to the global effort. This democratizes the search, vastly expanding our collective listening capacity. Similarly, the Galileo project has developed an app that turns old Android phones into powerful all-sky meteor cams. An old phone, often sitting in a drawer, can now be repurposed to continuously scan the night sky, capturing optical data, identifying moving objects, and feeding those observations into the same AI networks that analyze the Dalek camera data. Every new node, every additional pair of eyes or ears added to this burgeoning network shrinks the blind spots in our planetary observation system. AI doesn't care if your data comes from a sophisticated observatory in the Atacama Desert or a repurposed smartphone in a backyard in Lagos. Correlation is correlation. If an anomaly is observed from multiple, geographically diverse, low-cost sensors, its credibility skyrockets. You are not just a passive observer anymore. You can be an active participant in potentially the greatest discovery in human history. The Skeptic's Corner. Extraordinary claims require extraordinary evidence. This is a bedrock principle of scientific inquiry, and absolutely it should remain so. It's what prevents us from chasing phantoms and ensures rigor. But AI, in a profound way, flips the adjective in that statement. It doesn't make the claim less extraordinary. It makes the evidence ordinary. It presents the evidence as just another line in a CSV file, a time-stamped data packet, a statistically analyzed probability score. The evidence isn't anecdotal, blurry, or subjective. It's objective, verifiable, and machine-generated. This allows the extraordinary claim to stand on its own, supported by data that is, in its presentation, entirely mundane and reproducible. Skeptics traditionally argued that absence of evidence is evidence of absence. If we haven't found anything yet, it must mean there's nothing there. This was a reasonable stance when our search methods were rudimentary, our instruments limited, and our data processing capabilities primitive. But now, the absence is rapidly evaporating. We are no longer dealing with a complete void of information. We are down to handfuls of unexplained signals per million stars per month. We are seeing thousands of unexplainable aerial tracks every single month. At that density, staying skeptical, clinging to the idea that there's nothing out there, means betting against exponential curves. It means ignoring the overwhelming statistical shift brought about by our new tools. Good luck with that, because the data is telling a very different story. The universe might be vast, but our ability to listen and watch is finally catching up. The cost of being wrong versus the cost of being late. Let's consider the two extremes. Assume the worst-case scenario. Every single candidate's signal, every anomalous track, every whispered anomaly turns out to be terrestrial in origin. Perhaps a new type of military drone we didn't know about, a novel atmospheric phenomenon, or an as-yet unidentified natural radio source. Even in this worst case, we still end up with an incredible net gain. We would have cleaner radio catalogs, free of our own interference. We would develop vastly better interference maps, allowing for more efficient use of the radio spectrum. Our aerospace safety databases would be dramatically enhanced, potentially saving airlines fuel by identifying rogue reflections or previously unknown atmospheric conditions. The net cost of this ambitious search, even if we find nothing extraterrestrial, is effectively negative. We gain invaluable knowledge and infrastructure that benefits humanity in countless ways. Now, assume the best-case scenario. Just one signal is real. One confirmed, unambiguous techno-signature. The technological dividend from reverse engineering even a modestly smarter compression algorithm embedded in that signal, or understanding an advanced propulsion system from an observed UAP would pay for a century of astronomy budgets. Imagine the breakthroughs in energy, material science, communication, or even fundamental physics that such a discovery could unleash. The economic, scientific, and societal rewards would be incalculable, transforming our civilization overnight. Therefore, delaying this search, clinging to outdated methods, or allowing skepticism to breed inaction doesn't avoid risk. In fact, it guarantees missing out on an unparalleled reward. The cost of being wrong in this endeavor is negligible, yielding significant terrestrial benefits. The cost of being late, of hesitating, of failing to invest in this new era of AI-driven discovery is potentially the greatest lost opportunity in human history. We stand to lose nothing but our ignorance and gain everything. The cultural tipping point. Culture, like water, always finds its level, and increasingly it's being shaped by the relentless flow of data. We're witnessing a cultural tipping point regarding the question of UAPs and potential alien encounters. Remember 2017? The Pentagon quietly dropped 3 grainy black and white videos of what they called unidentified aerial phenomena. For many, they were just blurry images, and late-night hosts had a field day, turning them into punchlines. It was still largely a fringe topic. Fast forward to 2022. Congress held open, public hearings on UAPs, not behind closed doors, not in hushed whispers, but with elected officials questioning defense intelligence experts on national television. The tone was serious, the questions pointed. The conversation has shifted dramatically. Now in 2025, the cultural impact is undeniable. Marvel is reportedly filming a UAP miniseries, integrating these mysterious phenomena into the fabric of popular storytelling. On platforms like Twitch, streamers are hosting Find the Fleet Nights, where thousands of viewers collectively pore over publicly available sky camera feeds, tagging anomalies live, sharing observations, and collaboratively searching for anything unusual. This isn't just coincidence. Pop culture doesn't lead the data, it follows it. As more credible, machine-verified data emerges, as institutions like AARO and ESA legitimize the search, the cultural narrative inevitably shifts. AI-generated thumbnails on video platforms already favor phrases like classified leak or unexplained footage because algorithms learn what content drives engagement. This creates a feedback loop where transparency and genuine data-driven revelations are rewarded by algorithmic feeds, pushing more of this information into the mainstream. This cycle is irreversible. In an age of ubiquitous sensors and instant communication, attempts to suppression or secrecy are futile. If the military were to hide a significant sighting, you can bet that TikTok creators would recreate an Unreal Engine within hours based on leaked descriptions or eyewitness accounts, and those recreations would go viral. In this hyper-connected, AI-driven world, truth becomes the only truly competitive content. The harder you try to hide something, the more the digital world will try to expose it and visualize it. The next 500 days are packed with milestones that promise to accelerate this search even further. Each one a lottery ticket with increasingly better odds. By March, the Galileo project will finish installing 16 more Dalek nodes across the Southern Hemisphere. Why the Southern Hemisphere? Because it offers a largely unobserved window into our skies, away from the dense population centers and existing observation networks of the North. This expansion will significantly enhance our global coverage for UAP detection. In April, Breakthrough Listen, already a giant in SETI, will deploy AM-Auto-M, automated machine learning, on the Meerkat array in South Africa. Meerkat is a powerful radio telescope, and integrating AM-Auto-M means that the AI will not only process data, but also automatically optimize its own algorithms, learning and adapting in real time to find ever more subtle signals without human intervention. Then, in August, the European Space Agency's JUICE probe will begin its gravity assist past Earth on its journey to Jupiter's icy moons. Crucially, JUICE carries an AI experiment specifically designed to distinguish between mundane moon reflections and structured light flashes. This is a critical capability for future missions exploring potentially habitable moons, ensuring that any optical anomalies detected aren't just natural phenomena, but truly intriguing signals. Each of these milestones represents another leap in our observational capabilities, another refinement in our AI tools, another tightening of the net we cast into the cosmos. Each is a lottery ticket with better odds than the last. If even one of these tickets hits, if one of these projects yields a confirmed, undeniable discovery, the decade will end not just with a Nobel Prize, but quite possibly with a parliamentary holiday declared worldwide. It would be a moment that transcends science, politics, and culture, uniting humanity in a shared, profound realization. The question you're already asking. So after all this, the question lingering in your mind is probably, should I believe we're about to meet aliens? And my answer is, believe is the wrong verb. Belief implies faith, a leap without evidence. That's not what we're talking about here. The correct verb is measure. And what do the measurements tell us? They tell us there are 8 unexplainable signals flagged by a neural network, 2,400 unclassified aerial tracks per month behaving in ways we can't explain, and a statistical probability of coin toss odds, 50%, that we hit a confirmed technosignature before 2030. These are not beliefs. These are data points, statistical probabilities, and observed anomalies. So the conclusion is stark, yet simple. Either the universe is whispering to us and we are finally developing the ears to hear it, or our instruments are systematically hallucinating in ways we don't yet understand. And for the very first time, we have an intern, artificial intelligence, who never tires of checking, who never stops listening, and who is relentlessly pushing the boundaries of our perception. Conclusion. The call to action. If this story feels bigger than just another YouTube rabbit hole, that's because it is. We are not just observing a scientific endeavor. We are witnessing the construction of humanity's first planet-wide sensory cortex, and artificial intelligence is serving as its intricate network of neurons. It's a collective awakening to the vast possibilities around and beyond us. If you found this compelling, if it sparked your curiosity, please like the video. That small action helps the algorithm nudge more people toward empirical curiosity, toward engaging with data, rather than just speculation. Subscribe if you're ready for update videos the moment, literally the millisecond, those ache signals reappear or a new track defies physics and is confirmed by multiple sources. Be part of the first to know. And definitely hit that bell icon, because history might not send out a formal press release when humanity makes its greatest discovery. It may just log a CSV row, a data point that changes everything. Finally, a truly personal call to action. If you've got an old phone, an unused Android device sitting in a drawer, consider pointing it at the sky tonight. Download the Galileo app or similar citizen science initiatives. You don't need to be a scientist. The next alien encounter might not start with a giant radio dish or a presidential address on TV. It might just start with your cracked Android uploading a 3-second clip, a piece of data that breaks the model, that defies all explanation. When that happens, when the data finally speaks unequivocally, we'll be here, live, decoding it together as a species finally ready to listen.